ideally both datas are, we will gather it from the experimental thing only. Okay, so using a uniaxial tensile test like that, you'll be able to see this kind of specimen, right? Like we will set it on the UTM machine. So using this data only, we will collect all this data. Okay.
Yes.
Now, why this things is actually sounds matters. Do you know exactly like what is the term of what is the use of Young's modulus? What this values is exactly telling to us? Young's modulus.
Mm, like how stress and strain is varying,
Mm,
like
okay.
its proportionality.
Mm, okay. Means in general by using a okay, now like in structural steel has some sort of Young's modulus in terms of MPa.
Mm.
Like if I put it in the MPa means like I have 2 e power of 5, and then when I add aluminum means I'll be having different. So significantly, by just seeing the value, what I'm getting out of it, like what exactly this term is. I'm not stress strain relationship is there. Okay, so we'll keep it ahead of it. But what exactly I'm getting out of the
Strength
data?
parameter.
Yes, exactly. So it's ideally pointing out the how stiffer the model it is. I mean the
Mm.
whole component it is. Like the lesser the
Mm.
value, so the lesser stiffness the model it is having. Like
Mm.
more the value, like the more stiffer the model. So it will just given the resistive stiffness, like the way it is getting deformed. So ideally, like
Mm.
how it's actually working is it's a derivative of, I mean, normal tangential modulus. We will get it out of the stress strain curve. Like if
Mm.
I want to draw a typical stress strain curve, how it will
Mm.
works means. So this is the x-axis and this is
Mm.
the y-axis. So over here, like you'll be able to see I'm
Mm.
having strain. Okay,
Strain.
so here I'm having the stresses.
Right.
Like if I know, like when we started to apply the load, the stress strain relationship will be like this only, right? So it
Mm.
will go in that way. We will put it in a different color. So this we already explained. Like generally we
Mm.
call it as this is the A point and then B point. After that
Mm.
only non-linear nicking will happen. But in
Yeah.
reality, how it will happen is no, not exactly it will happen. Like before the we generally call it as this is a starting point and this point is a B point. We usually call it as a YTS, like yield strength of the material. But this limit is called a proportional limit. And after that,
Mm.
one some sort of point will be there, and then
Mm.
one more point will be came. So this point is actually the ultimate tensile strength. Then after that, the
Mm.
curve will go okay like this, and then the what happened here is this is the UTS, and it will go, and this is the F point, that is a fracture point. Okay,
Mm.
so here it is YTS and UTS. So this is a typical data we used to get it from the uniaxial tensile test.
Mm.
So we will fix. Okay, no, not fix exactly. Like either we will fix with the help of fixation, and then we will try to separate them into two pieces. So in that situation, we will get. But in reality, Ansys can't accept this kind of data. That's the problem we have. As we discussed earlier, like the term Young's modulus is a slope of this line. It's nothing but the slope of
Mm.
this line. Like we know that this is the Hooke's law region.
Mm.
Okay, so because the stress and strain is actually proportional to each other within the elastic limit. Okay, so we know that up to the proportional point only, the stress and strains are in a proportional way. After that, it won't be in a proportional way. And also one more thing, we all know that like these are all elastic limit. So which means like in between this line, like if we remove the load means it will come back to its original state. So that's what it is here. So by using this thing like run and rise approach, like you can see uh, what do you say, like E will be the stress divided by strain. That could be the relation. So because the running area will be, because we know the slope formula, right? Slope is equal to run over rise. So this is very fundamental, but I'm just remembering you like so the y direction will be the run and then the x direction will be the rise. Okay, so we have the run value will be the up to this thing, like it is the yield stress. It's nothing but like we are both of them having the same thing. So we usually this y will be the UTS value. For structural steel, it will be 250 MPa, and then strain, the elastic strain limit will be there. So this is the relation between the Young's modulus and then stress and strain. So it's nothing but the slope of this particular line. So why I'm remembering these things means, you know, there is a term called Young's modulus, but the moment when I added bilinear isotropic hardening, it is asking you a two different thing. So one is the yield strength, and another one is the tangent modulus. So now we have two different parameters. One is Young's modulus is there, and then tangent modulus is there. So unless you don't understand what exactly the Young's modulus means, you can't able to calculate the tangent modulus. It's very easy for me to tell that, okay, hey Subhushri, if you want to calculate the tangent modulus, you will just need three parameters. One is the percentage of elongation of the material, and you need the UTS, and then the yield point of the material, and then ultimate point of the material. Just go ahead with this formula like UTS value minus YTS, and divide the whole value by the percentage of elongation of the material. So that could be the standard formula, but where exactly this formula is came and then why we are using it is the matters. Okay, so now we'll understand from this concept. As I said earlier, up to this picture, everything is okay. Okay, now how can I feed this data into the answers? Okay, whatever you are seeing in this picture is the true data. I'm sorry, it's the engineering data. But for your understanding, do you have any idea about what is exactly engineering data and then true stress data?
Actually, I'm confused with the term, but what I know is
Mhm.
um, he, in one of the term we use the complete area, that
Okay.
is B by D, and
Mhm.
in I guess in a true stress we will use the area as an instantaneous area, like whatever the elongation
Yes,
or reduction of area is there.
is exactly. So
Hmm.
you're correct. So actually, what is the difference between it means engineering data and we have true data. Because we need to convert the thing like whatever the experimental, if someone is giving you the experimental data means obviously it will be on the engineering data only. It is not a true data. Okay, so we need to convert the data. So the general thing, the formula would be the this only. So engineering data is the load, which is nothing but the P. So stress, we know that it, right, like load
Hmm.
upon the area, so which is the original cross section.
Hmm.
So cross section will not be updated, but we know that when the load is incremented, so the shape of the cross section will get reduced. So when it comes to true data means it's load upon instantaneous cross section. Okay, now we got this pointer. So now we know that, okay, these are all fine. But how can I convert it? Because in general, this data will be like this only, right? But how a true engineering data will looks like, na? True engineering data in Ansys, you can't enter a curve in this manner. Means a non-linear curve, it's going to be bended in such a way. A non-linear curve will always be goes in such a way, like it will go this way only.
Mm.
Okay, so
Mm.
I mean, generally, if you see, you will see a slope, but not a
Um,
negative value. Okay,
yes.
so you have to do it because these conversion is happening because of the conversion of engineering data to true data.
Mm.
Okay, so this is true data. Okay, let's put it in a clear view. Okay, so what could be the basic formula? So this you need to note it from your end because the moment when we receive the engineering data, you have to create an Excel sheet and use this formula to for the conversion. Okay, so for stress,
Mm.
so stress is pretty simple. So what you need to do is like you have to like if you want to convert the YTS or UTS, whatever the stress value, that is an engineering stresses means stress. Okay, so in a short form, I'll mention it as a engineering stress should be multiplied with 1 plus E value. So what is this E? So E is the what is that star? E is equal to the percentage of elongation.
Mm.
Um, I mean, what exactly the percentage of elongation? Percentage of elongation is nothing but that's the failure limit of what it says a particular material.
Mm.
Okay, so let's say PB PBT. Okay, so we have this ultra derma, so I'll click on it. So we'll choose any material, some randomly. This is a plastic, so which is a combination of PBT and then PBT G50. So I'm just taking the data. So I'm just showing you how I'm taking the data. Okay, so open an Excel.
Mm.
Okay, so out of it, what we need to do is you have to go to this, and here you have a couple of inputs. Stress at break. See the material properties. Stress at break is 170 MPa. What is this
Mm.
stress at break? It is the tangent modulus is there. Stress at break is there. This is nothing but the ultimate point because in the stress and strain curve. I mean, again, I know that like it seems like what it say solid mechanics theoretical session, but
Mm.
there is no other option because unless or until we can't cross this kind of topics means in the evaluation of the results it could be very hard. Okay,
Yes.
so that's why I'm just insisting this kind of data. Okay, uh, okay, fine. So this is the UTS. After the because from the YTS to the UTS travel, model will experience a plastic deformation. but it will not get started to small crimping. I mean, after it crosses the UTS means the real failure will get started. Okay, till
Hmm.
the UTS also you can use it. Like a model will not break, but it will experience some plastic deformation. Okay, so that's why here they mentioned the stress at the break will be 170, which means that is the ultimate tensile strength of the material. And what is the percentage of elongation means is the strain at the break. Okay,
Hmm.
so they mentioned it as like a 1.6 percentage. They mentioned in terms of percentages. So which
Hmm.
means that could be our plastic strain limit. Uh, Percentage of elongation is 1.6 percentage, means we need to divide this thing by 100, so that we will get the strain value limit of 0.016.
1.6.
Okay, so mm mm. So where this value will use is if you are plotting plastic strain uh, output in the answers means, so you need to set a failure limit. So this could be the failure limit. Like the maximum value that I get it in the plot is greater than this value means, then I'm damn sure that okay, this component is going to be failure in the specific location where it crosses the 0.016 value.
Hmm.
Okay, so that could be the simple calculation. Okay, so the percentage of elongation is nothing but the strain at break of the component. Okay, that you need to take it from the outside. So this is the formula in order to convert the engineering, I mean normal uh, stress into a true stress. Like this is engineering stress. Let me put it in the way that it's true stress, because we are converting into a true stress, right? True stress is equal to the engineering stress multiplied with 1 plus E value, that is the percentage of elongation. Okay. Now true strain. So unless or until we don't have the true stress and then true strain means we can't able to calculate the bilinear parameters and then multilinear parameter also.
Hmm.
Okay. So when it comes to the true strain means, it's pretty simple. We need to take the log of the this parameter 1 plus E. 1 plus E will be common for both things, but there we will multiply it with the engineering stress. Here we just take a log of this parameter. Okay, so in YouTube's or in Google, like you will search these things like E and all, you know about it. So I don't need to repeat it again. Okay,
Hmm.
so I mean, what is the reason behind this formula? Like if I go behind that formula means, then it will be more solid mechanics session. Okay, so I don't want to get into too deep out of it. So let's see whatever it is needed for our session. Okay, so this could be the basic thing, like true stress and then true strain has to be calculated in such a way. So accordingly, I asked you to open the Excel. Nah? So from there, like you need to open the Excel, and here we will get couple of datas. So you see, so these are all general datas. Stress strain datas will be there. So when it comes to a non-linear data, if I want to take a non-linear data means, we have to take a look at in this graph. You'll have a couple of shear modulus graph is there, and then secant modulus is there, and then this secant modulus, shear modulus, these are all nothing but like they are all different parameters. Okay,
Hmm.
but as of now, what I need is stress versus strain. So you see, we have a stress versus strain graph over here.
Hmm.
So I can, here we have, and then here also we have like this is something different. Like we need this data only. I'll just take a zoom out of it. Okay, we have stress strain data in a different temperature. 40 degrees Celsius is there, 22, 23 degrees Celsius is there, and 100 degree, and then 150 degree is there. So for a room temperature, we need the data in the 23 degrees Celsius. So I'm just clicking out the 23 degrees Celsius. You'll go to the control points. You'll click on the control points over here and move the slide up to this point. Now, in the 23 degrees Celsius, you have the strain data versus stress data. Like suppose if I go to the answers, now I need to add rather than adding a bilinear isotropic hardening, I'm deleting it off. I'm just adding a multilinear isotropic hardening. Okay. Now you see in multilinear isotropic hardening, in the top right side, it is asking for the plastic strain versus stress data. Plastic strain versus stress data. So you will go to the particular page. Let's assume this is our data. I'll take all this thing and copy, and you go there, go to the answers, and you have to paste it over there. Now you see one graph is generated, right? But it should not
Hmm.
zero, because in logically you think that when you will get zero plastic strain based on this graph, when you will get zero plastic strain.
On
This
the
is elastic
elastic
strain.
limit.
uh, where it is starting, because here it is starting. So in this point only
Yes.
it is starting. After that, plastic deformation, plastic strain is there. Before that, this is
Hmm.
elastic limit.
Hmm.
So elastic, and this is plastic strain. Okay, so epsilon uh, E and then epsilon P. Okay, that's great. So means the elastic strain could be the yield pointer. So you have to enter the yield stress at this location. Let's assume that, okay, on this material yield is something different, but from here itself we can able to see the yield point also. You'll go to the top, you'll see the yield of the material. Most probably, or else like we can take the first data as an yield. Okay, so let's which is very closer to the 80 MPa, like let's say 60 or 70.5 Pascal. I'm just entering.
Hmm.
Okay, and one more thing you need to remember, you have to set the right unit system. Okay, because I believe that these are all in MPa. Okay, yeah, these are all in MPa. Now the data has been set in the Pascal. So I'm just repasting all the data after changing the thing, and then I'll 80.5. I'm just entering. Now we entered the data. See, uh, these data is a engineering data or true data? Whatever we copy and pasted it right now, na? These are all engineering data or true data?
I guess we will.
It's engineering data. Actually, it is engineering data. We
Okay.
have to convert this thing into a true data. So that is why we have seen this kind of
Ah,
calculation.
yes.
Okay. So unless like we directly have the true data in the online available means, because those are all, so remember that whatever the data that we get it all, na, so those are all in this format only. Okay, so
Okay.
it will give you in this manner only. Okay, so that's the problem. So that is why we need to use it. Like using the Excel sheet, you have to incorporate this formula. Okay,
Hmm.
so I have the formula data within me. So might be I'll share you this data in for your future references. Like you can, all you need to do is you just need to paste the engineering data. So automatically it will convert it into a true data. So then after that you have to copy the true data to the answers itself. So this is how you have to build a multilinear database of a material, because getting a multilinear data is like a very tedious process. Like this is how we need to do the backend process, and we have to create our multilinear data. Multilinear data only will give you the more reliable result. Okay, so otherwise you simply put Young's modulus, because if I come to the thing, like so many people will tell that, okay, sir, my simulation result is actually not matching with the testing data, or else like they will come up with a different kind of, not only the in our cases we are dealing with something different. Okay, but when it comes to plastic simulation or whatever it is, they have some enclosure and then they will do the simulation and experimental data is not exactly matching with the simulation data. They will come up. The fundamental reason is because we are not providing the proper input data. Okay, there is a lot of assumption in the simulation itself. Okay, so numerical method is an approximation approach. So there itself, if you are compromising on the data means, then we will have a too much of deviations. Okay, to avoid that deviations only, maximum whatever the possible inputs that we can give into the software, we have to give it in a very true format. Okay, other than that, like in linear, there is no other properties is there, only three inputs are there. In fact, that is two inputs only. Like one is Young's modulus and then the Poisson ratio. So Young's modulus only tell you the stiffness behavior of the whole material. So since it's an isotropic material, that's the only input. And then Poisson ratio, lateral and then longitudinal deformation ratio it will give. So other than that, there is no other parameters is there. Shear modulus and then bulk modulus will be calculated based on the Poisson and then Young's modulus. So forget about the stress strain curve. So those will helpful in the, even some material will not come up with the stress strain parameter data also. Okay, so yield and ultimate is only for our purpose only, reference purpose only. Okay, so in nowhere else the yield point and then ultimate point will take into the calculation. Okay, so these two parameters are the linear material parameter. So that is why it is very important to define the plasticity of the model. Okay, so now one thing I want to clear in this point, that we are purely talking about the ductile material only. Okay, so for brittle material or hyperelastic material like rubber related things, the story will be completely different. Okay, so I mean the definition of plasticity, methodologies and then approaches will be completely different. Okay, so that's the key difference between it.